So today we're going to talk about the Riemann zeta function, one of an important function in analytic number theory. So it was initially introduced by Euler in the case of real numbers, and then later Riemann extended it to a meromorphic function on the plane. So, so Riemann Euler zeta function. And so it's initially defined as follows. You take a real number, a positive real number, and you define, a number bigger than 1, and you define the sum of 1 over n to the s as n goes from 1 to infinity. Okay. And you see that for s bigger than 1, then this is a convergent series. It's pretty easy to see that if we change this to complex numbers and look at the complex numbers whose real part is greater than 1, then you also have a convergent series. The reason being that if you look at n to the negative s, well, that's the same thing as that is by definition e to the negative s plus s log n. If you're looking at the size of that, well, that's going to be e to the let's say s is that this is sigma plus tau I, the real and the imaginary parts. This is going to be negative sigma log n. In other words, you get n to the negative sigma, right? So as long as the real part is bigger than 1, then this is well, let's say it like this. As long as the real part is bigger than some 1 plus delta, bigger than some 1 plus delta, then you know that the size of these terms is controlled by 1 over n to the 1 plus delta, right? And since sums of this form converge, well, then that by wire stress m-test gives you that that this converges uniformly, right? So this we know that on 1 plus 2 on the right hand side, on the right hand plane, past real part with real part greater than or equal to 1 plus delta, we know that we have uniform convergence, right, by wire stress m-test. And so so we have convergence to a holomorphic function on that half plane, and then we can take delta to be any number bigger than 0, and so we get that the function is holomorphic on the half plane past where the real part is bigger than 1. Okay, so that allows us to think of the function on in that region. Right.
Sorry.
Do you have a class?
No, it's okay.
Okay, thanks. Okay. Now going back to the Euler's version, where s is bigger than 1. Euler. So what's the connection between this and primes? There is so-called Euler's identity. And so that says that, in fact, the zeta function can be expressed as 1 over 1 minus p to the negative s, where p ranges over all primes. Okay, so you can, that if you take this product, this infinite product over all primes, in fact, you can you recover the zeta function. Okay, and so the idea is as follows. You say, well, look, if you look at these guys, 1 over 1 minus p to the negative s. Well, that's a geometric series, right? That's a geometric series, which is going to give you. It's a geometric series for it's the sum of a geometric series, right? Okay, and so if we take the product, over all primes, well, what kind of things are you going to get? You're going to get things like you get a sum. One gets a sum of all terms of the form. And this is not rigorous, but if you took an infinite product of this infinite series, then you would get a sum of all terms of the form 1 over some prime to some power times some other prime to some other power. You get products of primes to different powers. Right. So you get all possible terms of this form, but by the fundamental theorem of arithmetic, every number has a prime decomposition, right? So what you get when you take all terms of this form is you get all natural numbers, right? So sorry, there should be s's here. Right, and so what do you get? So you see that every natural number can be has a prime decomposition, right? And so what you get is a sum of all numbers, all natural numbers to the s power, right? Namely the zeta function, right? So that's the idea, and you make that you can make that precise. You can make that precise in the following way. You say, okay, so well, why is it true that that this actually equals this? Okay. So first off, you say, well, no. So fix n and n, positive integers, where n is bigger than n. Okay. You say, well, now let's consider the sum 1 over n ds, where n is less than or equal to n. Okay. Right. So each such n can be written, can be expressed as, like we said, as some p1 n to the n1, p2 to the n2, pk to the n sub k, where all the primes are smaller than n, right? Because n is smaller, right? n is n is less than or equal to n. So of course, all of this, the primes have to be less than or equal to n. And further, the powers all have to be less than m. M is bigger than n. So all the powers have to be less than or equal to m. Right? Because otherwise you get something bigger than n. Okay. So what does that tell you? So if we consider then this product of the form 1 over p sub s for primes that are less than or equal to n, if we look at this finite, this finite product 1 over p ms, right? Then that will give us all of the numbers. That will give us all of these terms for n less than or equal to n, right? And more. So we see that we get this n less than or equal to n. Okay. Now if we let m go to infinity, we get this is less than or equal to less than or equal to this, right? And then let n go to infinity, and we get that the zeta function is less than or equal to that infinite product over all primes. Right? Okay. So in the opposite direction, we do something very similar. We say, well, look, if we consider the full-blown zeta function, well, that's going to be greater than or equal to the product up to ms, again for p less than or equal to m, right? Because this is going to give us, some terms up to a particular point, but no further, right? And so then, just as before, we let m go to infinity. We let m go to infinity, and we see that that this thing is bounded by the zeta function. And then we let n go to infinity, and we get the other inequality. Okay, so we get equality. Okay. Okay. So in any case, that's just sort of like a connection between. In any case, that's a connection between the zeta function and primes. Okay. Okay. So let me go backwards. Okay, so what we'd like to do is get an analytic continuation of zeta to all of C. And that's going to be kind of tricky. So what we're going to do, the way we're going to do it is to try to get the following equation, the following functional equation. So our goal is to get this functional equation that pi to the negative s over 2 has a gamma function at s over 2, zeta function of s equals pi to the negative 1 minus s over 2, pi 1 minus s over 2, zeta 1 minus s. Okay. This will basically allow us to get to extend the zeta function to the entire plane. Okay. You notice that there's some symmetry. There's some symmetry to this statement, and later on we're going to define this thing as something called xi. So this, in the terms of xi, it's saying that this is kind of symmetry. That xi of s equals xi of 1 minus s. Okay. So in order to get there, we're going to need some results about something called the theta function. Let me define what that is. So for t bigger than 0, we let theta of t equal summation e to the negative pi n squared t, and n equals over all integers n. Okay. You may be wondering why I use this strange looking theta rather than the usual theta. So there's actually something called the Jacobi theta function, for which one uses the capital theta, and then there are a couple of variants of the theta function. This symbol is actually used for a different variant, so we have to use this symbol. Just a second. Okay, so let's get that. Okay, so this is the theta function, and you see that that this converges. You've got this definitely converges on for t bigger than 0. Okay. Okay, so what we're going to get is this equation, this functional equation for the theta function, and it looks like this. Okay, so theta of t is equal to t to the negative half theta of 1 over t. And the proof of this relies on a calculation that we did a long time ago in using contour integrals in chapter 2. It was the following, that e to the negative pi x squared, e to the negative 2 pi I x c dx equals e to the negative pi c squared. Okay. So this function we call g of x, e to the negative pi x squared. Then what this says in terms of for the Fourier transform is that the Fourier transform of g equals g. You're taking the function, you're integrating against this character, and then you see that the Fourier transform of this function, the Gaussian distribution, is just itself. Okay. So we're going to use this formula. We're just going to play around slightly with this formula in order to get Fourier transform for another function. So we'll let f of x be just a scaled and translated version of this function. So it'll be e to the negative pi t x plus alpha squared. Okay, and what we'll see is that the Fourier transform of that equals t to the negative 1/2 e to the negative c squared over t e to the 2 pi I c. Okay. Okay, so what that will give us, so remember the Poisson summation formula. That the sum of the function over all integers equals the sum of the function, its Fourier transform over all integers. Right? So just plugging that in, you see that that will give us that summation e to the negative pi t n plus a squared over all integers equals t to the negative 1/2 e to the negative pi n squared over t e to the 2 pi I n and a with a summation on it over all integers. Right. If we take a to be 0, this thing turns into 1, and you see that what we get is well, this thing is the theta function, right? And then this thing is the theta function evaluated at 1 over t times t to the negative 1/2, right? So we get theta function equals t to the negative 1/2 theta times theta at 1 over t, right? The functional equation. Okay. So so to get that, we need to get this. Okay. We want to see that the Fourier transform of f actually looks like that. So. So we get that from this expression. Okay, and we do it. We get it via a change of variable. Okay, so just let x turn into t to the 1/2 x plus a. Okay, so what do you get? Straightforwardly, you get e to the negative pi x squared, so t x plus a squared, e to the negative 2 pi I x c dx, but dx is going to be t to the 1/2 dx. Right? So just substituting, right? And then we evaluate it at c over t, at c over the square root of t. Okay. I don't know if I should rewrite it, but so we get e to the negative pi t x plus a squared, e to the negative 2 pi I x plus a c t to the 1/2 dx equals e to the pi c squared over t. And then, so this looks kind of like the Fourier transform, but we need to just like clean it up a little bit. We want e to the negative 2 pi I x c dx. We move everything else to the other side, right? So we get e to the 2 pi I xc t to the negative 1/2 e to the negative pi c squared over t, right? E to the negative pi t x plus a squared. Okay. And so you see we get that the Fourier transform of f is indeed t to the negative 1/2 e to the negative pi c squared over t times e to the 2 pi I axc. Okay, so it's just this is the same formula. This is the same formula. Okay, so okay, so what is that good for? Right. The point was that we wanted to get that what we just did plus Poisson summation gives you this expression for this functional equation for the theta function. Okay. Now. We're basically going to use the theta function we're going what we're going to need for the theta function is to have some control about the behavior of the theta function as t goes to infinity and as t goes down to 0. Okay, so here are the necessary bounds that we get. Okay, 1. As t goes to infinity, the theta function minus 1 decays like e to the negative pi t. And 2, as theta goes to 0, the theta function is bounded by some constant times t to the negative 1/2. These turn out to be very, very straightforward estimates. So the proof of one is that, well, you say, look, this theta minus 1 is just e to the negative pi t squared. I'm sorry, pi n squared t as n goes from negative infinity to positive infinity, but n is not equal to 0. Right? Just subtract off the zeroth term. At least this is this expression is even in n, so we write it as twice the sum e to the negative pi n squared t from as n goes from 1 to infinity. Now this thing e to the negative pi n squared t and goes from 1 to infinity is bounded above by e to the negative pi nt, right? Because n is smaller than n squared, right? But now this is a geometric series, right? So so we get 1 over 1 minus e to the negative pi t, right? Minus 1, right? Because we're missing the zeroth term. Okay. If you work that out, that's 1 over 1 minus e to the negative pi t times e to the negative pi t, and t is going to infinity, so we just assume that t is bigger than 1, then this is bounded above by 1 over 1 minus e to the negative pi. so we get the bound that we want, right? We get that the difference between the theta function and 1 goes to 0 very fast, right? So as t goes to infinity, this function goes to 1. Okay. Now, the second part, to show that as t goes to 0, we have this sort of thing. Well, you just use the functional equation. The functional equation says that this is t to the negative 1/2 times theta at 1 over t. As t goes to 0, well, this thing goes 1 over t goes to infinity, which means, as we just saw, that theta goes to 1. Right, and so we can definitely make this smaller than twice t to the negative 1/2. Okay. Okay. So okay. Yeah, actually, I should have done this part earlier. So I'm going to rearrange. This in the video, but should have done this earlier. Okay. Okay, so let me go backwards a little bit. So, okay, so we showed that that this expression converges for when the real part is bigger than 1, right? So that the zeta function makes sense, on the half plane, from 1 onwards. There's a way to extend, so plane, we can extend zeta to the half plane going from x equals 0 onwards. Okay. And we'll do it in the following way. You say, okay, so the zeta function is the sum of these terms 1 over n to the s, right? Right. So if we look at the function 1 over x to the s, okay, then the zeta function, right, is the sum of these areas, right? The sum of these areas, right? 5, 6, 7, etc., etc. Okay. So define delta sub ns as the difference on the nth interval between 1 over n to the s and 1 over x to the s. As the integral, defined as the integral of the difference over that nth interval. Right? So s tells you how what curve you're using. Okay. So right. So excuse me. So observe that when the deltas of n are entire functions, And this is for the same reason that we've said before. We can invoke that theorem about integrating, taking averages of holomorphic functions, and then still getting a holomorphic function. Okay, and two, notice that by construction, 1 over n sub s, if we take the sum from n equals 1 to n minus 1, right? The sum from n1 to n minus 1, and subtract off the integral from 1 to n of 1 over x to the s, then we just end up with the sum of the deltas from n equals 1 to n minus 1. Okay. So, so how do we use this to extend zeta to to the right half plane from 0 onwards? If we can, what we're going to see is that, so maybe I should just do it. If we let f of x be x to the negative s, and consider it on x, I'm sorry, on n plus 1, on the integral n plus 1, then the mean value theorem gives you that 1 over n to the s over 1 over x to the s is controlled from above by absolute value of s over n to the real part of s plus 1. Okay, so so what does that give you? So as long as the real part of s is bigger than 0, then we see that this well, actually, I have to be a little bit more careful. As long as the real part of s is bigger than 0 and s is controlled by some constant r, then we see that that this is, again by a wire stress M test, this thing converges uniformly and thus to a holomorphic function. So this converges to a holomorphic function. Okay. Now that's on as long as we stay away from 0 and we stay inside some disk, right? But we can do that. This thing converges to a holomorphic function on any such disk, any such chopped off disk, right? And so we can take r as large as we want, and s is close to 0 from the right hand side. I'm sorry, the real part of s is close to 0 as we desire, right? And so we have that it converges to a holomorphic function on the right half plane past where the real part is bigger than 0. Okay. So this converges to some holomorphic function, which we'll call h sub s there. Okay. So now we come back to here, right? We come back to here and we let n go to infinity. let n go to infinity, we get that, I mean, we get that for, if the real part of s is bigger than 1, then this thing is going to turn into the zeta function, right? It doesn't make sense otherwise yet, right? This thing is going to turn into 1 over s minus 1, and this thing on the right turns into h. Okay. So, so we have this gamma of s equals 1 over s minus 1 plus h, as long as the real part is bigger than 1. Okay. But this expression on the right actually makes sense for as long as the real part is greater than 0. So what we do is we define, we just define the zeta function to be this thing on for the real when the real part is greater than 0, right? And that gives us an extension that allows us to extend zeta to that new domain. Okay. So yeah. So this is apparently like kind of the more straightforward way of extending it, but it, yeah. Yeah. So this is one way of extending the zeta function, and apparently you can use it to extend the zeta function to the whole plane, but maybe it's more difficult than doing it by Riemann's method, using the functional equation. Okay, so I think I'm going to stop